Hello and welcome everyone to our webinar today. Today we'll be talking about the equipment validation in art laboratories with our speakers, Martine and Nijs, the Director of Professional Education at CooperSurgical, and Dave Morroll, the Director of Clinical Support in CooperSurgical as well. Thank you, Dave and Martine, for taking the time to join us today. And we'll hand it over now to you, Dave. Thank you.
Thanks, Amir. Just give me one moment while I share my screen. Okay, hopefully you can all now see that. So welcome to this webinar on equipment validation. As Amir said, I'll be starting the webinar. I've been around in embryology since 1986 and I'm currently Director of Clinical Support at CooperSurgical. And I'll be joined by Martine, and perhaps Martine, you could say a few words about your background.
Yeah, thank you, Dave, and welcome all to this webinar. My name is Martine. I'm the Director of Professional Education currently in CooperSurgical. I joined CooperSurgical roughly 5 years ago, and before that I had a very long career as a clinical embryologist, a researcher, a teacher, a lecturer, and a lab director and scientific director in different clinics. So yeah, I hope that I can bring you some interesting inputs on the validation of equipment. Dave?
Thanks, Martine. So as you can see, we've got quite a lengthy experience, so we're hoping to share some of that today. And what we're going to talk through is, first of all, start off by explaining what validation is and why we might choose to validate. And then what we'll try to do is focus in on how we validate equipment, how we do it, what it involves, when to do it, and then we'll talk about some specific examples. And I will start, and then at some point I will hand over to Martine. So let's take a quick look at what validation is, and you can look around for various technical descriptions of it, but essentially what it is it's confirmation of plausibility for a specified intended use or application through the provision of objective evidence that specified requirements have been fulfilled, and that's taken directly from the ISO 15189 standards for medical laboratories. And what it means is when you validate, you set out what the intended use is, the specifications that a particular piece of equipment needs to meet, and then of course the objective evidence is based on testing, measuring and making sure those specifications are met. Now you've probably already seen this. This is the general overview of the stages of validation or qualification of equipment. DQ, IQ, OQ, PQ, so design, installation, operational and performance. And design qualification is obviously what you're setting out right at the beginning when you are buying new equipment, what it's intended for and what sort of performance is expected. Installation, as the name suggests, is when you're putting that equipment into the lab, making sure it's installed and does what it's supposed to. Operational qualification is testing that it's operating at those specified levels, and performance qualification is more around testing how a piece of equipment works under real life conditions. And I guess that's the one we tend to focus on more because it will be done initially, but also it's part of the revalidation of equipment from time to time, which we'll come back to. And just bear in mind that when we validate or qualify equipment, it's really critical because that feeds into process validation. If we don't have appropriately qualified and validated equipment, then process validation falls down as well. So just to go into that a little bit more detail, as I said, the design qualification, and we're going to use the example of an incubator. The design qualification sets out the purpose, which is typically culture of gametes and embryos. We want it to be appropriately certified, whether that's a CE mark or an FDA approval or whichever is appropriate. We want to know that we've got the right sort of size and numbers of equipment. And of course, for incubators, we know that we'll be setting specific criteria like temperature, gas mix, humidity, and so on. And then the installation qualification is about where we're putting it, making sure it's arrived and is installed in good condition, that it's appropriately calibrated, that we've got an operating manual. And of course, people need to read that operating manual and know how to use pieces of equipment. And we'll also want the backup elements, so the guarantees, the warranties, the service schedule, and so on. In terms of the operational qualification, that's around getting that newly installed piece of equipment to the point where it's usable in our case, in the clinical setting for our embryology procedures. So it means cleaning it, checking the functions, make sure it's appropriately set up to the required set points. And of course, those are user set. We'll come on to that later on. We want to make sure people are appropriately trained in any new equipment, and there are SOPs that cover its use. And we also want to investigate the process limits. Where will it allow us to modify things, and where will it become a problem? And importantly, part of the operational qualification is making sure we understand what will happen if things go wrong. So we will typically test, again in the example of an incubator, that alarms will sound if the door's left open, or if the temperature goes too high or too low, or the gas mix fails, or the CO2 level is too low. Where appropriate, we want to know what the effect is of a power failure. So how long will it maintain temperature and pH of our culture system if we have a total failure in mains power? And if appropriate, will the battery backup operate successfully? So that might be in terms of the UPS, the uninterrupted power supply system, or it might be an integral battery backup system, such as we see in the BT37 incubators that we supply. So we want to understand what will happen in worst case scenarios. And then in the performance qualification, that's around making sure we understand that everything's working as it should for conditions that mimic what we would be doing in the lab. So we'll look at temperature mapping, pH testing, VOC testing, and then doing mock procedures to test how that works in normal use. So for example, in a box incubator, you'd want to see the impact of repetitive openings of the door, for example. Where it's allowed, you would do a mouse embryo assay. If you can't do that, then a sperm survival test to check that there are no residual VOCs that might impact the quality of our gametes and embryos. And of course, as an ongoing performance qualification, we should assess our KPIs to make sure that things are working appropriately. Now, why should we bother to go through all of this? Excuse me. Well, if you look at, there's a number of different resources here, but we're looking at the EU data for serious adverse events that apply to tissue banks, in particular reproductive tissues and cells. And what you can pick out from all of this data is that around about 10% of the serious adverse events are due to some form of equipment failure. So that's not an insignificant number of events that contribute to really poor outcomes potentially for patients. So making sure that we understand the risks and how to deal with the risks, and mitigating to avoid risks is really important. And of course, it's also worth mentioning that in terms of why we validate, it's also good laboratory practice. It's a central element of quality management systems and good laboratory practice. And if you go to any number of guidelines, regulatory articles and so on, such as the EU Guide to the Quality and Safety of Tissues and Cells for Human Application, good practice guidelines for IVF labs, whether that's European or not. There's a whole raft of guidelines and so on that state that you should validate equipment. And of course, it might come into the way your lab is accredited or certified. So this is taking some examples here. These are the ISO standards. All of these cite equipment validation as part of the requirement for the lab to be properly accredited. And the one that is most pertinent to IVF labs generally, again, is ISO 15189. That's actually been updated to a 2022 version. But all of these require you, as part of your accreditation or certification to a standard for ISO, require you to validate all of your equipment. So what does it involve? Again, we're going to use the incubator as an example. This again is taken from one of the appendices of this EU document, the Guide to the Quality and Safety of Tissues and Cells for Human Application. This is a 2022 edition. You can search for that online and it gives you a whole range of information. We picked out this appendix because it's a specific example of a qualification of an incubator that you can follow. And the key things to pick up on here is, first of all, on the first page, it will ask what that piece of equipment is for. What is the equipment intended to do? So here we're talking about incubators that will be used during processing and culture of samples. The other important thing to mention is that it will then ask you to detail that specific piece of equipment. So who supplied it, who's the manufacturer, what's the model, and most particularly, it will ask for the serial number. So this is a really critical point, that when you validate equipment, that you validate each individual piece of equipment. You cannot assume that if you validate one G210 incubator, for example, that all of the other G210 incubators will do the same thing. It has to be for each individual piece. And then it says details of testing levels and methods used in validation. This is where you're setting out what your validation will be testing. So typically here, given that your IQ, DQ, IQ and OQ will have set CO2, oxygen, temperature, typically as the parameters that you want to control, your equipment qualification will also test those. So it then sets out what you would do during installation qualification. So you can see here it's around, has the equipment arrived undamaged? Is it where it's been put, will that adversely affect clean room airflow if that's relevant? Have you got an instruction manual? Have you got certificate of conformance? Have you got a warranty? And so on. The operational qualification, this is the bit we get more involved in, I guess. It is around testing the functions of the incubator. Do the switches and the buttons do what they're supposed to do? Do they work? If it's got shelves, are they fitted correctly? Have you got an SOP for using that piece of equipment? Have you got records of it being appropriately cleaned and swabbed? And then, of course, the bits that we tend to focus on, which is setting temperature and CO2 levels. So again, you've got to understand what the target values are, and then test that they are being met. And then the performance qualification, which, as I've said, is the one that we are interested in terms of reflecting real world performance. So this is around temperature mapping empty. You might repeat it during use. You've got testing and connection to alarms, your CO2 levels, and it's not just about setting the target CO2 levels, but as you might just be able to see here, at what point do your CO2 levels elicit an alarm? So if you set your CO2 at 6%, does it alarm at 5.9%, 5.8%, 5.5%? So you'll need to decide what that low level alarm is, and similarly, you'll have a high alarm limit, and you'll also need to think about delay times. So delay times are really allowing you to go in and out of incubators without always setting off the alarm. You might think about humidification, and you'll also potentially go on and do pH testing, which we'll come on to. So if we accept that validation is a good idea, and we think that it's going to help us set up things properly, when should we do it? Well, there's a number of different scenarios in which validation should be done. The first thing is, as we've said, according to guidelines and the ISO standards and so on, you may have to do it in a way that makes sure that you're compliant with your local regulations, with the ISO standards, or whatever standards that apply to your laboratory. And in that case, as we'll come on to later on a little bit, that might stipulate when and how often you need to do this validation and revalidation. And the frequency of that revalidation probably depends on how critical the equipment is. So, for example, we know how important incubators are to IVF labs. So that inevitably will potentially lead to revalidation more commonly than some other less important pieces of equipment. You'll certainly be required to validate new equipment when it comes into the lab, because you want to know for sure that it's performing appropriately. And then you will also revalidate or validate if equipment is modified. So that when we say modification, we're really talking about any significant changes that might impact safety or quality. So anything that might significantly affect what we're doing, that needs to be retested. And just be aware, it's not just the equipment, it might be the software, but it also might be the way that piece of equipment is used. So again, it's linking the equipment validation to the process validation, because they are inherently connected. The other thing to say is that it's good practice to revalidate after servicing or repair. So we tend to focus on servicing as a way of making sure our equipment is working well. That servicing needs to include some degree of revalidation, recalibration. So it may be done as part of the service. So that's part of the discussion to have with your service engineers, your service company. The critical thing here is making sure that any service or repair, where adjustments or new pieces of equipment or new parts, we need to make sure that they won't impact what we do. They won't impact quality and safety. And then, of course, you may well be aware that ISO accreditation is all moved now to risk-based models. So if you do risk assessments, and you feel there's an increased risk, you would automatically trigger an additional validation process. What about examples? And I'm going to talk about the lab environment and the HVAC system. So this is a really interesting one because we see variations from lab to lab when they revalidate air quality, and this is taken from a couple of documents. There's the Cairo Consensus document that you're probably all aware of, but I've also taken it from, again, the Guide to Safety, Quality and Safety of Tissues and Cells for Human Application, and this particular part is taken from an article from O'Donoghue. You can find this online. Validating and monitoring the clean room. It's in a handbook for critical cleaning, and what this sets out is the suggested schedule of tests to demonstrate continuing compliance for your air quality. Now this is targeted much more towards standard clean rooms, so that's the caveat that I would say to this, but I think it's still applicable. And what it says is that the essential elements of your validation of your air quality monitoring are the particulates, as you would guess, because it's numbers of particulates that dictate the grade, airflow, so the volume and velocity, the air pressure differentials, and the air change rate. So this is fairly standard stuff for clean rooms, just thinking about the cleanliness of the air and how often it's changed, and whether you've got a positive pressure in your embryology lab. The optional tests include whether you've got any issues with your filters, whether there's a problem with room temperature and airflow direction, relative humidity, lighting and noise. So more general information about your work environment, the room, the clean room that you're working in. And what it says overall is that for the essential elements, if you're working at very high levels, and we're talking about class 5 ISO or higher grade, then you should be doing it at least every 6 months. For those of us, and in IVF labs this is more typical, you'll be in ISO grade class 6, 7, 8 and so on. Every 12 months is probably okay. But that's a maximum time. Remember, that's a maximum time. So it should be no more than a year that you retest, revalidate your air quality. And the 12 months also applies to your airflow volume and your pressure differentials. The other optional ones can be every 2 years. We know that the air quality isn't just about particulates. So if we look at the other elements, the microbial load, we would typically there validate by testing at rest. So in my practice, what we used to do is one embryologist would come in very early in the morning, set out all the agar plates around the lab, and leave them open for about an hour before people started working. Those would be collected, and then we'd do the same thing during the working day. So we had at rest and in operation. And you can see again from the same paper from O'Donoghue that we've got recommended limits for microbial contamination. What we would typically expect to see is that if you're working in a well-controlled workstation, it would be at grade A. And then the background might be higher. Particularly what we found is the pass-through between procedure rooms and lab was a particularly dirty area. The key element here is you would do this periodically. We certainly did it monthly. I know some labs will do it less frequently, We did it monthly, but the important thing is that you increase the frequency if you find you are repeatedly out of control limits. And you can use the information to target key areas and make sure you do the testing to pick up the busiest times. Excuse me. The other element that's really critical to excuse me, to embryology labs, of course, is VOCs. And here we have a particular focus on aldehydes, but total VOCs is an easier way of testing, sorry. And you're probably aware from the Cairo consensus that the less than 500 micrograms per cubic meter, or 400 parts per billion is an easier way to look at it, is the lower threshold for acceptable levels of VOCs. So we need to test 2 parts per billion level. We would ideally look for different VOCs rather than total VOCs, but that sort of testing is actually not particularly easily to do routinely. It's worth doing once in a while, particularly in a new lab. But for retesting, probably the total VOCs is the way to go as a routine test. And that's often done with these handheld photoionization detection systems like the Grey Wolf. What about the culture environment? I'm going to talk about temperature, pH, and humidity. Now, in terms of temperature, we will typically do all of our cultures at 37 degrees. There are some papers out there suggesting a slightly lower temperature is preferable, although there's no clear evidence of benefit. And that's based on the fact that actually the core body temperature is typically lower than 37 degrees. And temperatures within the female reproductive tract are even lower, typically 1 to 2 degrees, although that is dependent on the time in the menstrual cycle, because as you're probably aware, around the time of ovulation, the core body temperature actually rises. The key point here is that we're likely to be setting at 37 degrees, but it's up to individual labs to ascribe a set point and the tolerated range for temperatures, depending on what they're doing, of course. So we tend to focus on incubation and culture of embryos, but remember that might be different during manipulation. So, for example, room temperature during vitrification, we need to think about control in different ways. And also be aware of the things that alter temperature. So the source of the heating, the type of vessel, we'll come on to that in a moment. So I mentioned vitrification. Also be aware that for sperm things are different. So we tend to avoid 37 degrees as much as possible during handling and preparation. Just some examples then. This is taken from a paper by Walker and colleagues from a decade or so ago. And what this showed is in a typical box incubator, they actually tested 2 former box incubators. And what they reported is that depending on where they tested, they got slightly different temperatures. So you can see front left was 36.92, but it could get as low as 36.64 at the back of the middle shelf. So just really to show that there will be small differences across incubators. We also see it to some extent in bench tops, less, but still possible. And just be aware that these are the temperatures when the incubator is closed, and repeated opening has a further impact, as do recovery times. The one piece of data I could find from Neil Stoddart and colleagues published way back in 2003 suggested that actually these small differences have no clear impact on outcomes. But I don't think we should be complacent. We need to be aware of these issues and just deal with them appropriately if we can. Probably more of an issue are the heated stages. So this is taken from a Nijs study, again from quite a long time ago, 2002, by Cook and colleagues. And what they did here is they looked at temperatures over time on heated stages. So they had a couple of different setups along with an ICSI chamber. So this is the polystyrene chamber that sits around an ICSI microscope. Now they deliberately set that at 35.5 degrees to avoid overheating, which if you read the paper is quite interesting because they clearly had a problem with the piece of equipment and yeah, probably not the best starting point. And what you can see, it's a bit difficult for you to see all of the different symbols, but what it's, the take-home message from these is really that over the course of a couple of minutes, all of these dishes, they set up standard dishes at 37 degrees, put them on the heated stages, and they all lose temperature over time. So after 3 minutes, you can see that they're down at around 36 degrees or so. So what they noted was that cooling was affected by ambient air temperature. It was affected by draft, so airflow. And of course, airflow was also linked to movement of people. So if people are moving around, you're more likely to see cooling. And what they also stated was that if you are able to leave lids on dishes, if you're not doing manipulations, or if you can use larger volumes, those are both protective. So they slow the rate at which temperature decreases. Now, a similar, more recent study from 2020 by Kokakali and colleagues actually tested 4 different types of dishes. You can see a typical ICSI dish, small culture, large culture, and the big 19mm dishes. And what they did here is they checked temperature at 3, 5 and 10 minutes on a heated stage at 37 degrees and preset at 38.5. And again, what you can see is if you have a look at the lines in the same color, they will all decrease over time. So at 3 minutes, they'll drop, and they'll drop from the starting temperature at 37 degrees. And what it shows here again is that if you have a starting temperature on your heated stage, it is more protective. But it's also important to note that you have to do the temperature mapping to make sure that that higher starting temperature isn't going to cook the gametes and embryos that you put on them. So they are likely to cool down. So in this case, it's an ICSI dish that's on a heated stage at 38.5 and it's relatively well controlled, but it will decrease over time. So this decision to go to 38.5 is protective, but that decision to use 38.5 is something you need to test and validate in your own system, depending on what sort of dishes and volumes of dishes you use. Now, when it comes to ICSI, this is a nice paper where they showed 3 different systems. Everything was set up to 37 degrees. There were 3 ICSI setups. System 1 and System 2 are effectively the same, but System 2 had a heated objective lens, whereas System 3 is a different system, but mimics System 1 in some ways. But the critical point here is System 1 and System 3 didn't achieve the same results as System 2. And what this illustrates is that by heating up the objective lens, you avoid problems with cooling caused by the large objective lens underneath your ICSI dish. Now, of course, when you do ICSI on an inverted microscope, the objective of the inverted microscope is very close to the underside of the dish, and therefore it acts as a heat sump and causes cooling. And this is demonstrated here this is a thermal image of a heated stage on an ICSI microscope with an aperture, and as you expect, you get cooling. Now, if you see the same thing with a heated glass stage, you still get this cool spot in the middle, and again, that's because of the objective lens acting like a heat sump and causing cooling right over the area where you'll be working. And that's why we use the thermosafe system, this system of blowing warmed air onto the underside of the dish to solve that problem. It warms the objective and it keeps the underside of the dish warm. Now, you can do a whole raft of temperature mapping, and as we've suggested, your incubators and your heated stages need to be tested. Just be aware that there are different impacts of different probes. We typically see type T and type K thermocouples, that's these two here. These are made primarily of copper, and copper is a fantastic conductor, which means that it's very sensitive, but also what it also means, it's very prone to fluctuation and procedural areas. So if you use a thermocouple like this and it has a tiny exposed wire at the end, that's the bit that you might typically put into microdrops when you're testing. But if the rest of the thermocouple is cooling, you might be under measuring. So you just have to be really careful that you're not under measuring with that sort of system. A PT100, which is made from platinum, is much more stable, but it's harder to use for some testing such as heated stages. So perfect for in incubators where it can sit there and warm up, and it's great. But in a heated stage, you can't put all of this probe onto the heated stage and get a reliable measurement. Just be aware again that however you choose to do it, ambient temperature potentially has an impact. What about pH? We know that the embryos typically are at 7.1, which is why we use 7.2 to 7.4 to avoid acidosis. And we know that some stages of embryos are particularly vulnerable, mature oocytes, post-cryopreservation oocytes and embryos are particularly vulnerable to pH change. So we want to make sure that this is kept as stable as possible. And the way we can do this is typically we'll use a pH meter, a blood gas analyzer, or you can use fluoroscopic systems. The fluoroscopic systems are really the ones that we use for continuous real-time testing rather than spot tests. So it would be more typically a pH meter or blood gas analyzer. Bear in mind, if you use a pH meter, it should be one that's temperature corrected and suitable for high protein solutions. Percent CO2 is not an ideal measure for pH. We can use both. The partial pressure of CO2 is more relevant than percentage. But if that's the only system you've got, then it's better than nothing. But ideally what we're going to do is use a pH system and test directly. Now, what to test and how often should be based on lab practices, but typically it will be when we introduce a new batch of medium or we're testing new media. That's the minimum requirement. And then humidity, quickly going to mention this. It is ideal if you can test humidity in your background air. The Cairo consensus said it should be 40 to 45%. That's quite difficult to control unless you've built in systems into your air handling unit. We know that low and high levels potentially have their downsides. What we would also say, of course, is that if you are using dry incubators, you just need to factor that in. There is some evidence that humidified incubators improve outcomes, but that's only really true if you don't take the appropriate steps. And the bottom line for humidity control in microdrops, even if you're using dry incubators, is that you use an appropriate amount of oil. So if the volume of oil and the thickness of oil above your microdrops is adequate, your control of humidity of your microdrop should be absolutely fine. Okay, I'm going to hand over to Martine at that point, and she's going to talk you through the next stages.
Okay, great. Thank you, Dave. And I will continue just organizing my screen as well here. So yeah, the next example is going to focus on micromanipulation. And micromanipulation, Dave already talked a lot about the heated stage. And I will focus more on the micromanipulation itself. And some principles that he explained as well in the beginning is that you need to know what the equipment is for, the intended use. Now, the laser, for example, the intended use, why would you use the laser, is to do assisted hatching or zona thinning, to do laser-assisted ICSI, to identify immotile sperm, to open the zona pellucida for biopsy, and to weaken the cell junctions when you are biopsying trophectodermal cells. So this is your intended use. And during the whole process, you are selecting the best laser system. And here are some criteria you could use as what is for your setup the best laser. And for sure, that will be an active laser, so you don't need to move your embryo or your cells to the laser, sorry, but the laser will move to the intended point where you want it to laser. We want a visible laser, so you know where you're going to hit. High power, because that is a more efficient one and the safest one. It should also be safe for the operator. The imaging needs to be there, needs to be compatible with your microscope and the other brands that you're using on your ICSI or micromanipulation setup. And that's another criteria you could choose for, is that you are going to work with a foot pedal. So intended use, why am I going to buy that laser, and what are my criteria are really key in defining that validation process. So how can you then see if it's working, it's doing what is intended to do? So this is a really easy way to validate your laser, and this is using a glass slide or a Petri dish. Put black marker on these, and then you will focus, you will indicate the target where you want to laser, and that is this crosshair here, the red crosshair. We will laser, and if we are hitting, if the marker is being burnt away where we have intended it to be, then you'll have a correct laser setup. If that is not the case, and this is the second example I'm showing you here, that you have a deviation of the point where you want to laser, where the actual lasering is being done, then this is a danger for all your operations that you will do with the laser. So you need to then align the laser. So it's an easy way to test just prior to each micromanipulation setup before you start the lasering. So the laser alignment, and I'm using the Saturn example, this is an active dynamic laser. It will move to different points that you indicate. So how does it work? Well, it's 7 calibration points that you will confirm. It will move to these 7 different points, and that is so quick. As you can see, it's not even 1 minute, and you have done your laser calibration before you continue your work, and you're sure then that you are hitting where you want to hit with your laser. Another important aspect of the validation and checking the quality of the working of the laser is to look at the hole size. So there is a link to the intensity of the laser beam, and that works with time. So a laser beam is 300 microseconds, for example, or 600 microseconds or less. And depending on the length of exposure, the size will be of that hole will be different. Normally, this is your service engineer that will do this hole size calibration, but I'd like you to understand the principle. And so what they do is they use a zona pellucida of a non-fertilized oocyte. It needs to be fixed really at the level that you're doing your micromanipulation. You focus on the zona, and then you start lasering with 300 microseconds, for example, and then you can measure the hole that you have there. And then you go to 400, then you go to 800, etc., and you can have this graph as indicated here, the hole size calibration. But this is also really important to know if you want to define the intensity that you use, for example, to make the cell junctions for TE cells weaker. So you don't need to use 600 microseconds. You can go to a lower intensity, 200 microseconds, but this should be then validated on your own setup. It cannot be taken from a paper. You have to check in your own setup how many microseconds that will be. Another part of your micromanipulation setup that really needs to be validated regularly, especially also when it's new, is your injectors. And that's really easy. You install a pipette, you dip it into a medium or into PVP, you aspirate the medium, and you see if you can control the medium, if it stays stable, so that there is really a balance, a stop, that you have this menisc where you have a stable control over what is happening in the pipette. So if there are bubbles present, then it's not okay. So then you need to clean perhaps, or refresh the oil if it's an oil-based system, or you need to look if there are crisps in there that came off the glass. So the validation of that of these injectors is also very important and really easy to do. Make sure you log all these validation processes. As Dave nicely showed in the beginning, the example for the incubator, you can set this up for your micromanipulation setup as well. Now let's look at the cryo storage system. This is a huge environment. This is our bank, and it has so much precious materials, oocytes, sperms, embryos, testicular tissue, whatever. So we are safeguarding those materials, these tissues and cells in our cryo storage. When you buy a new one, so this is another approach for new tanks, you really have to inspect each tank when they arrive. The dewars need to be inspected on the inside, on the outside, if there are no damages, if the lid is fitting well, if the canisters fit well in there. And as well, as Dave showed as well, you need to get all the information, the serial number, the date of manufacturing. You could even write that on the outside of the tank. Also, when you start using the tank, because you will remember, but you should have also a formal, or in your software or on a hard copy, a sheet for that specific dewar. Then you will weigh the tank, and if it's a dry shipper, you will fill it up, tip it over so that the liquid nitrogen goes out, and you will empty this, and then you will weigh it as well, and then you will have your starting weight. And the weight is really a great tool to validate if you have leaks, if there is a stable evaporation over time. Of course, there will be evaporation. And this is also a tool, a parameter that you need to measure is the mass evaporation rate. So you will weigh, you fill up the tank, you put in the canisters, you close the tank, you weigh it, and then you will leave it for several weeks and weigh every week, for example, and see how fast the weight is changing. You can then convert that to a volume, so you can then change it, and you will know how many liters of liquid nitrogen have evaporated. And you need to compare that then to the evaporation rate that the manufacturer has given to you. That is normal for that specific dewar. So these are tools, easy to do, but they need to be planned. They need to be planned and be done regularly as well. Another important one is to look at the daily use. You will not have these dewars sitting there and you watch them. No, you will be using them. You will be opening them. You'll be taking samples, adding samples, etc. So you also have to check how that influences the quality of that dewar, the cryo storage safety of that dewar itself. The alarms, also very important. You have to check and validate if your integrated alarm is working. So that means you need to have add an extra alarm and then create an alarm. So leave the tank open, for example, and then see if they correlate. The external new alarm and the alarm that is sitting in your tank, and see if they are alarming when there is a problem. Working with large cryo vessels is different than working with the closed dewars. So if you have a large storage tank, there are two types. There is the wet tank and there is a dry tank. Now, a dry tank is never dry. There's always a certain volume of liquid nitrogen in there. And so here you will also have to define the changes in temperature when you open that tank, because it's normally a large opening. And the group of Kobo and Tether, they really looked into that, and there are changes. So you need to check and define how long you can open the tank before there is a critical temperature change. In my previous clinic, this was 5 minutes. So when 5 minutes, we put alarms, and after 5 minutes, the alarm would go, and they had to close the tank and wait until it is equilibrated, stabilized again inside the tank. Also, but this is not validation, this is good laboratory practice, don't put your vitrified samples on the top layers, but in the middle or lower. So practically, there is a different approach to working with the dry tank, which has some liquid nitrogen in there, and then with a fully tip-top liquid nitrogen tank. But it's up to you for your system to do that validation and see what are the best laboratory practices to work with these. This is your cryo storage environment. So it's not only the dewars, it's also your security access that you need to validate if it's working, your oxygen alarms, your force ventilation. So create situations that are alarming and check if that really works. The emergency button, you have to validate if it's doing what it's supposed to do when there is an oxygen alarm, for example, or when you are in need of help. The tanks, we discussed right now the tank alarms, so you have to check those as well. And then your backup system, of course, you need to check if the generator will switch on, because you need that for your forced ventilation. And if you have a UPS system, also you have to do that at least once a year. The filling system can be manual, that's easy to check, but you have to check if your tank is full, so you have to log all of that. If it's automated, you have to still continue to do manual checks and validate. If you have a system where it calls automatically to the company that the truck will arrive and tips up your tank, you have to create a false alarm or false order and see if things are happening. So you have to validate that as well. And then there is all the software linked to that, so your lab information management system, and also your samples themselves. They need to have traceability. You need to know who owns these samples. Have they been paid? Is there informed consent for what happens to these samples in case of divorce or donation or whatever? So there are tools to help you with that, but still you need to validate if that is working. And that means you could do hypothetical cases. You do audits as well to see if all is in order. Last one that I will discuss is computerized systems. We often think we buy this software, it works, we're not responsible, we'll just install it. No, you as a user, you have a big responsibility. And the EU guides that Dave also mentioned in his presentation clearly states that the type of software that we use, computerized systems, belongs to a certain category. That's the category 4. That means that we need to have a risk-based approach and check our supplier, number one, to see if what are the risks associated with this supplier if we buy the software from that company. And then also demonstrate on a risk base that the application is working within our own lab environment, not a test environment, but within your own laboratory situation. These are just a few points that you will do, but The guide will really guide you through the whole procedure. And the blue boxes here are the ones that are for the customer. So for us, for you, is that risk assessment to make the validation plan, but this is in collaboration with your supplier. And then you will also have to, again, what are the requirements? What are your user requirement specifications? And then you will check and double check and see if it is all working as it should be. An example, for example, electronic witnessing system. There you will have everything recorded, who is doing what, where, when, and how, and with what. And that will ensure the traceability for you. And to validate that system, for example, you will collaborate with the supplier. They will help you. You have to define, however, your critical witnessing points. And you have this process flow that you will define in collaboration with the supplier. You will still run in the initial phase a manual witnessing system during a short period, and then see where there are clashes or where there are weak points in your witnessing. And so you will identify those missing witnessing points. You will have to check how data is entered. If you report, you look for reports, if everything is in the reports, and then you will see and double check, validate if it is integrated in your own clinic's electronic patient management system. And also you have to validate if your backup system, if there is a blackout and you cannot use this software, that you have a solid hard copy back or whatever backup system that you can use. A lot of information that we've given to you. So let's summarize and then we'll take some questions if time is left. So it's clearly stated and nicely defined, although it is very theoretical in the ISO 15189, that validation is the confirmation of plausibility for a specified intended use or application through the provision of objective evidence. And this evidence is obtained by observing things, by measuring things, by examining things in your processes, your equipment. And we can then confirm that the specified requirements have been fulfilled. Now, IVF is a process, so we should see it as a real that there is a real need for this validation and potentially also accreditation, of course. And each step and each variable of each process needs to be identified and controlled so that we will get a high outcome, high pregnancy rate, and healthy babies in the end. So validation needs to perform not only on our equipment, but also on the premises, the utilities, and also on our procedures. And we have to have this in a report form. And during the validation, in-process controls should be defined to monitor the process. So thank you very much. If you need more information, we have a great knowledge hub, and we're happy to take questions from you now. Thank you. I'll stop sharing.
Thank you, Dave. Thank you, Martine, for the very informative presentation. Now we're going to move to the question and answer segments. First question, for VOC meter situated inside the lab shows part per billion and not part per million. Is it okay to have to part per million and not part per million values? The second question, what lower value limit to be set for VOC meter if it cannot be converted to part per million by the manufacturer?
I think that's for Dave. You discussed VOC.
Yeah, I think it's a fair question. The really important thing with any VOC meter is that it does measure down to parts per billion. The parts per million really aren't sensitive enough. So again, if you reference the Cairo consensus, it might look a little peculiar because the reference values are 400 to 800 parts per billion. So that's 0.4 to 0.8 parts per million, which is why the parts per million testing isn't really helpful. The reason there's a range is that we know that there are certain VOCs that are more relevant than others, but I think you take the 400 parts per billion as the target value. Below that doesn't necessarily mean it's entirely safe. It's all about balance of risk. But if you're below 400 parts per billion, you're relatively safe. 400 to 800 is a bit of a grey area because it then depends on what sort of VOCs are there, which might need more testing. Over 800, you're certainly in the realms of it being way too high.
So Dave, can I ask you on that topic? Do you think there are specific areas in the lab where you would do the VOC testing? I'm just thinking of the off-gassing area or moments when you have cleaned. I don't know, please.
Yeah, absolutely. It's a really good point, Martine. I think, there are areas that are at greater risk, and the obvious ones will be where oocytes or embryos in particular are exposed. So when we're handling them without an oil layer, which we know is protective, for example, during vitrification. A good practical example from some of the lab visits we've been doing recently where we've taken VOC meters is that if you haven't got a good positive pressure system in your lab, cleaning in adjacent rooms like the procedure room, we've seen instances where people have started to clean ultrasound probes or wipe over beds in the procedure room, and you can detect VOCs coming back into the lab. So areas of cleaning and high risk areas are the ones that you would focus on, but you get an idea if you do VOC mapping around the lab, you'll pick up where the key areas are.
Okay, thank you. Second question, how can I validate my cryo alarm system?
How can you validate your cryo alarm system is to create an alarm. So as I explained, you could fill up the tank, add an extra alarm, and then by evaporation, see if at that specific level, don't bring your samples at risk, but at the specific lowest level, if the alarm is going off. And then if that is too low, you can increase the position of the alarm. So this is also more a test that you will do initially when you install a new tank, but you will have to repeat, and the repeat will be then to create a false alarm, leave the lid open under safe conditions, of course.
Okay, thank you. There's a question. Does the operation PQ and OQ fall under the quality management, which includes quality control, improvement, and assurance?
Yeah, I'm not entirely sure I understand what the question is, but the quick answer is yes, it's all part of quality management. The whole purpose behind DQ, IQ, OQ, PQ is to underpin your quality management system. It's a way of ensuring that each piece of equipment goes through the process of, so the design qualification is making sure that the piece of equipment you choose is actually suited to the purpose you intend to put it. Installation qualification is making sure it's put into place in the right area and it works, it's in good condition. And then the OQ and PQ is making sure that it operates to the specifications you set. I mean, it's worth emphasizing again that ultimately it's up to the user to design the specifications, much like as Martine said, when you're testing alarms, you've got to decide when it alarms and whether that point of alarm is appropriate. But essentially all of that qualification of your equipment at each stage builds into the wider quality management. So it's the DQ, IQ, OQ, PQ is for each individual piece of equipment, but that builds into your system of equipment and processes that underpins the whole quality cycle, quality improvement. Yeah, they're all intertwined.
Yeah, I can add to that as well that each and every operator, embryologist, lab technician, whoever is working with the equipment is also responsible to do the tests, as I said, that on a regular basis before you do an operation, before you do your micromanipulation or whatever, but also flag if things are not as they should be. So if they see temperature is off or too high or too low, they need to really raise an alarm to their lead person and investigate, and not work, okay, we'll look in this tomorrow, or we'll present it at the meeting. These IVF so sensitive techniques and high precision techniques that you need to be on the case time and time again. Yeah.
Okay. Second question for, she said, how about the hygiene monitoring? Is it no longer part of the QC for laboratories?
Oh no, it absolutely is. That's the microbial load testing that I referred to. So because of time, we didn't have a huge amount of time to dwell on it. But part of, we often concentrate on air quality in the lab and think about particulates. We're embryologists, so the VOCs are important. But the microbial load around the lab is of course an important factor to consider. And that's why, for example, we would do it monthly. I didn't go into the details, but we had settle plates for background air. We also did contact plates where you actually touch the egg. I'm not sure it was always agar, but you know what I mean, the agar plates that you use. So we understood where the risk areas were in the lab for cleanliness. And as I mentioned very briefly, we knew from our results, and this will vary from lab to lab, which is why you need to make sure you do it yourself. But we knew in our lab that because of our cleaning protocols, the workstations were always the lowest risk, and the high risk areas were the areas that were less controlled or more difficult to clean. So the pass-through hatches between procedure room and lab were always the dirtiest. Not terrible, but the dirtiest. And other areas that were high use and perhaps more difficult to clean, like around the ICSI microscopes, we also found needed more attention. And what that allowed us to do is make sure that we constantly reevaluated that and decided how we would improve our cleaning procedures. And of course, the ICSI rigs were higher risk because there's lots of wires and tubes and the air syringes, and it was the one procedure that people did a lot of setting up without gloves. We tended to wear gloves all of the time, but when you were just setting up the piece of equipment before the ICSI, you might do it without gloves. So it's a case of doing the appropriate tests and then highlighting where the focus needs to be for cleaning, but it will be those high traffic areas generally.
And your overall hand hygiene, your PPE, standard cleaning protocols, and you have to decide for your own situation, depending on the workload, the traffic in your lab, if you're a clean room or trying to be a clean room. So that all will define how many times, and also, as Dave said, you will identify those critical points where you know you will fail. But bear in mind, these cultures, microbial tests, they are like snapshots. So today, at that time you will do it, doesn't say anything about tomorrow at the same time. So that's why your overall standards of hygiene should be very high.
Okay. Other question, I found that the good blast at 120 hours to 122 hours post OPU, is it related to pH or anything else in my QC in the lab?
Well, that could be a whole raft of things. If you're looking at good blastocyst rates at 120, 122 hours, so that's day 5, isn't it? There are a raft of things that could potentially impact that. pH is one, temperature control's another. It could be how many times the incubator's open. There's a whole range of things, and that's why the quality management and KPIs, again, it's building up this system of having good processes, good data collection and data analysis, particularly through the KPIs that the the Vienna and Istanbul consensus documents give us examples of, and using that data to try and determine what factors are important. So it also builds into traceability. Is it linked to a particular medium or a particular batch or a particular embryologist or a particular workstation? So it's very difficult to necessarily pinpoint one factor. You have to control them all, and if you've got a problem, then you need to have the confidence in your data management for it to allow you to try and find a root cause when things are going wrong.
Okay. I think next question for Martine. Do we need to buy new cryostorage viewers when the warranty period is finished?
Ooh,
That's a good one.
that is a good one.
Do you buy a new car when the warranty is finished? No. So,
Okay.
no, but you can use the viewers after warranty, I think, and it depends on your own situation. How many times you're using this? Are you using this in a safe way? Are there any dense accidents with the viewer? So you will have to really monitor the longer post warranty. You will have to monitor more intense that tank, because at some point it will be too old and there will be leakage or evaporation. So I think the warranty is good because you can have a replacement or you can go back to your supplier. But after that, it's your responsibility to monitor and check if your tank is intact, if there are any dents or whatever. So it depends on how you use it and how many times you use it.
Okay. There's a question for you, Martine and Dave. This kind of action done by the embryologist as a traveler embryologist, or it's preferable from embryologist working in the particular lab?
Well, I would say it's very difficult for a traveling embryologist that comes in and does, either a daily work or comes in and just does biopsies, or my feeling would be that it's very difficult for that person to get a full picture of the quality management across the whole unit. So it'd be more.
I tend not to agree, Dave.
Okay.
I mean, if you do validations, you have a whole SOP, you have paperwork, you have set in discussion with the local lab or quality manager what the criteria are. I think it's doable. Of course, you need to have a training and induction into that lab, how things are working, when to do tests on the stage and what not to do, not influencing the workflow. But I think it could be done by somebody who is well trained, who could be external. If on the conditions I just mentioned, SOPs, criteria met, good interaction with the lab staff, etc. Sorry.
No, and it's a fair point, isn't it? Because it comes back to the same issue that you've got to have, you've got to have good process validation, you've got to have good SOPs, and you've got to have good data management that allows you to collect, analyze, and act upon that data. I just think that's slightly easier if you're on site, but I accept that it's doable.
Okay. There's a question. Do you really need to validate each and every heated stage? If I do, one from specific brand, is that representative for all stages of the brand, of that brand?
We know there's variability, so it's always advisable to test each individual heated stage. Just understand that there's variability, and just to give you an example, that we even see, for example, in some electrically heated stages, you'll see differences on the same surface. So you need to understand, for example, in some of the larger heated stages you get in workstations, you'll get slightly hotter, bit like the incubators, slightly warmer spots in one area and cooler spots in other areas. So you need to test individual ones and make sure that they're all tested appropriately.
Yeah, I agree. And also, each heat stage will not be under the same environment. One will be directly on an airflow, one will not be. One is close to an incubator might be heat giving warmer environment. So, yes, you have to test and validate each and every equipment. Yeah.
Oh,
Even
okay.
if it's from the same brand.
Okay. The question, is it possible to use the thermometer with the Cooper Ains, keep it in the incubator all the time to accelerate the measurement process?
Just repeat that for me again, Badar. That was
The one that the
copper.
thermometer with Cooper Ains,
Yeah.
if they keep it in the incubator to accelerate the measurement process because it takes like 1 minute or 5 minutes. They want to accelerate the process.
Yeah, with what you can, it depends on the incubator and the way it's set up, but you know, it's easier, I think. Now let me turn it up by the way. Yes, you can absolutely leave the probe in the incubator and constantly measure. Measuring temperature in incubators is relatively easy because you've usually got a chamber or you've got a box or somewhere you can put one of the thermocouples or temperature probes, and it's relatively easy. My preference is always to have a constant surveillance system, so that doesn't rely on the internal systems of the incubators, but you have a separate probe that's constantly monitoring as well. I'm a big fan of the monitoring systems that have independent probes to all of your key equipment all of the time. But sitting a probe in the incubator, yeah, absolutely, you can do that. And with the copper probes, the issue with copper probes is that they're more likely to fluctuate. If they're sitting in the middle of an incubator, that's not a problem. The issue with the copper probes that I mentioned is that they're more prone to fluctuation, but also the main issue is with when you're measuring microdrops rather than incubators. That's relatively easy. When you're testing temperatures in microdrops, that's more of a problem because they fluctuate. They're more prone to what's going on in ambient air, but also the copper wires at the end of a thermocouple can cool down the microdrop as well.
Okay.
Which is why you tend to get under measurement.
All right.
Thank you.
So, thank you, Dave. Thank you, Martine and Bloor. And thanks to
Thank
everyone
you.
who joined us today. Sorry for taking more time, but definitely we enjoyed the informative information shared. We still have a few questions we could not answer. We're going to respond back to you by email with our answers to your questions from Dave and Martine. And we're looking forward to see you next year, as this webinar, it's our last Middle East webinar for 2024. See you. Have a good day. Bye.
Thank you.
Thank you. Have a good day. Thank you.
Bye.
Bye. Bye.